Hi, my name's Graham Bao, and I'm a third-year physics major.
Hi, I'm Natasha Evans. I'm a first-year mechanical and aerospace engineering major.
I'm Elena Geiser, and I'm a third-year physics major.
I'm Ayush Patnaik. I'm a first-year mechanical and aerospace engineering major.
Today, we're presenting development of flight software and analysis tools for CubeSat attitude determination and control systems. So we're working on UC Davis's first satellite mission. The purpose of the satellite is to conduct experiments and take pictures of the Earth. But in order to do this, the satellite needs to know where it is and which way it's pointing. So our goal is to work on the software that helps that happen.
So the objective of our flight software is to make the satellite's attitude determination and control systems accurate, efficient, and fully autonomous. Using data from sun sensors and magnetometers, software will be used to determine the satellite's attitude or orientation. It will also be used for attitude adjustment by manipulating control hardware, including the reaction wheels and magnet workers. The software will also be open source in order to make satellite design easier and more accessible for others in the CubeSat community. We'll be discussing our attitude determination algorithm, Triad, and our control algorithms, BDOT and PID. First, I'll hand it off to Ayush to talk about our virtual sat, which is a dynamic virtual model of our satellite.
Yeah, so as Natasha said, virtual sat is a virtual dynamic model of our CubeSat created using the CubeSat mission planning toolbox on MATLAB, Simulink, and Python. One of the major challenges of developing satellites is to meet the exceedingly tight requirements such as attitude control, data storage, ground station facilities, orbital parameters, downlinking time, power, etc. Virtual SAT provides graphical representations of the aforementioned requirements that we need to design and plan our current and future missions. So it gives us a platform to see and study the behavior of the CubeSat under external factors like gravity gradient, aerodynamic drag, and test the implementation of the software and hardware present in our satellite. As you see in the control diagram below, the orbital parameters, reference sun vectors, and the physical properties like mass, inertia, equations for external force and torque, and the sample values from the onboard sensors on the satellite can be set and passed. For now, we are using maximum values for them. We are working on implementing dynamic external forces. As you see in the simulation below, showing the live graph consisting of latitude, longitude, attitude, and altitude over which it is passing. We are currently working on setting up the ground stations based on latitude, longitude on the model of the Earth, and see the amount of data transferred to the ground station and analyzing the power usage based on time spent in the light and dark phases of orbit. It will be very helpful in further optimizing and configuring the different parts of our CubeSat. It will also be useful as a test platform to test the Triad and the BDOT algorithms. I'll now let Graham talk you through the determination software.
The attitude determination software is necessary for determining the CubeSat's orientation in space, and Triad's our main determination algorithm. Its purpose is to output the direction of the CubeSat, the direction that the CubeSat is pointing. Triad takes in 4 inputs as shown in the diagram: the sun sensor data, the magnetometer data, the sun reference vector, and the magnetic field reference vector. And it outputs the angular state in the form of a quaternion. And the quaternion is basically just a mathematical representation of the satellite's orientation, and we use it to reduce the possibility of singularities in the data, and those are basically just invalid outputs from our algorithm. The Triad algorithm has been implemented in Python, and the 2 reference vectors come from reference models of the sun and of Earth's magnetic field. The sun reference model propagates Earth's orbit and rotation to calculate the direction of the sun relative to the Earth-centered inertial frame. And we've implemented this method in Python to take in the JD2000 value as input. And this value is just the number of days since January 1st in the year 2000. And it will output the direction of the sun as a unit vector. We compared some of the values calculated using this model with the values from the JPL database, and we found that there is a really small error between them. The magnetic field reference model uses the International Geomagnetic Reference Field package, PIIGRF, in Python. And by using this package, we can just input the latitude, longitude, altitude, and decimal date, and the output will be the unit vector estimating Earth's magnetic field at that point. Comparing the PIIGRF data to the NOAA magnetic field calculator, we also found that there's a very small error. The vector outputs from these two reference models, along with the sensor data, will be the input into the triad that will tell us the direction that the satellite is pointing. Now we'll have Elena speaking about using the BDOT control algorithm.
So the purpose of BDOT is to detumble the satellite once it's released. Essentially, it's used to tell the magnetorquers how strong of a magnetic dipole to produce, which makes the torque needed to straighten out the satellite. The way the algorithm works is shown in this flowchart. So first we calculate B dot, which is the time derivative of the Earth's magnetic field, and then we can calculate the magnetic dipole using B dot and a scalar constant K, which is used to optimize the detumbling time and is chosen by us. And then using this dipole, we can calculate the control torque that we need to help detumble the satellite. And we do this using the dipole crossed with the Earth's magnetic field vector. And then we can also, with the dipole, calculate the current we need to run through the coils to create this torque. And we keep doing this over and over until the angular rotation of the satellite is approximately 0, so it's no longer rotating. The inputs of this algorithm are the Earth's magnetic field vector and the angular rotation of the satellite, and the output is the control torque we need to apply and the magnetic dipole we need to make that torque. So the goal of the algorithm is really to get the current so that we can communicate it to the hardware. And right now we're currently working on a MATLAB simulation of the detumbling process so that we can find the best K for the optimal time of detumbling. And now I'm gonna hand it off to Natasha for PID control.
So in order to control the reaction wheels, we'll be using the PID algorithm, which stands for proportional integral derivative. The PID algorithm uses a feedback loop to continuously adjust the satellite's rotation rate to minimize the error between the satellite's current and desired angle. First, the PID algorithm must calculate the error between the satellite's current angle, which is calculated by triad, and the desired angle, which is pointing towards Earth. As shown in the diagram below, the output is the sum of 3 components. The proportional component is just the error itself multiplied by a constant Kp. The integral component is the sum of all previous errors multiplied by a constant Ki, and this component minimizes the steady state error, which refers to any small remaining error between the satellite's current and desired angle as the error approaches 0. Finally, the derivative component is the rate of change of the error multiplied by a constant Kd, which slows the satellite's rotation as the error approaches 0. The output is the sum of these components, which is subtracted from the reaction wheel's current rotation rate. So the angular velocity of the satellite increases in the other direction by conservation of angular momentum. The new angle of the satellite is calculated by triad and is once again used as input for the PID algorithm in a feedback loop. So the satellite's attitude is continuously and autonomously adjusted until it reaches an acceptable angle and rotation rate. So this graph shows a simulation of the PID algorithm running when the satellite is already spinning and pointed away from the Earth. The PID algorithm acts to change the rotation rate of the satellite so that it oscillates closer to its desired angle. As the error decreases, the oscillations become smaller, and the derivative component works to reduce the rotation rate. Ultimately, the PID output, CubeSat angle, and satellite rotation rate all approach 0, so the satellite is pointed towards Earth and stabilized. Testing will need to be performed in order to optimize the constants used in the algorithm, because larger values will result in a faster rotation rate, but also greater power consumption. So our goal is to make the reaction wheel control as efficient as possible. We also want to determine the maximum rotation rate of our reaction wheels and account for that in the algorithm, so that the reaction wheels aren't commanded to spin faster than they're capable. In order to integrate the software and hardware, we'll also be performing testing with actual reaction wheels using a float unit and air-bearing table, so that reaction wheels can spin freely as they would in orbit. Now I'll be handing it off to Graham to discuss the overall flow of our software.
All right. Here we have a diagram showing how the software connects with the control systems on the CubeSat. So on the left, here's the angle desired, which represents the direction that we want the satellite to point. Looking at the top branch, the angular velocity of the CubeSat, which is measured from the gyroscope, is input into the BDOT algorithm. And BDOT tells the magnetorquers to apply a certain torque, which causes the satellite to rotate. And now if you look at the second branch, the error between the angle that the satellite is pointing and the angle that is desired is input into the PID controller. The PID controller then causes the reaction wheels to rotate by a certain amount, and this also causes the satellite to rotate. As a result of these processes, the satellite is now pointing at a new angle and it has a new angular velocity, which is shown on the right. Triad measures this new angle and feeds it back into the loop. So this is a closed loop control system and fully autonomous.
So even though most of the framework for attitude control and determination software has been developed, but future work is still necessary for testing and integrating the software with hardware as well as the flight software. In the near future, the focus of the work will be on collecting data from the hardware tests and analyzing the uncertainty of our results. Later, end-to-end testing will be conducted using a Helmholtz gauge to simulate Earth's magnetic field and a sun simulator to simulate the sunlight. All software developed for REALOP's mission will have a large impact on future UC Davis students as well as the CubeSat community as a whole. All of the work that is done for this mission will be available to the future members of the Space and Satellites Club to build on and reference. The software will also be open source and will be available for other universities and organizations that are developing small satellites. By sharing our work, we hope that others will be able to learn from it and implement it into their own projects.
We'd like to thank Dr. Stephen Robinson for his continued support as our faculty advisor, Adam Zufall for guidance with the determination software and for his continued friendship, and Vamsi Ayuni for creating the framework for our ADCS software. If you have any questions, please feel free to contact us at the emails shown below. Thank you for watching and for your interest in our work.